Hey everybody, class J. Let me share my screen. So for class J, we're going to talk about similar triangles, really just so we can talk about how some other triangles are similar. And then we'll talk about special angles and then maybe reference angles depending on how long I take. So let's talk about similar triangles first. So what are similar triangles? Definition. Two triangles are similar. There's actually two different ways you can think of it. They're similar if they have all the same angles. So if they have the same angles. Alternatively, you can say that two triangles are similar if, I guess I put an or here, or if all the sides are in proportion to each other. So let me give you an example. To each other. I should finish my sentence here. To each other. So let me give you two examples. So here's one example of a triangle. We already know the 3, 4, 5 triangle. So here's my 3, 4, 5 right triangle. And this is definitely similar to this larger triangle. I'm going to draw it kind of differently. This 6, 8, 10 right triangle. And I can see that they're similar. I don't know what the angles are, although I kind of know what they are, but whatever. But I know they're similar to each other because every side here is in proportion to every side here, meaning 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So if each of these sides here is a multiple of one of each of these sides here, then you can say that the triangles are similar to each other. So you can take any triangle and multiply all the sides by whatever number you like and get a similar triangle. So for example, I'm not going to draw it to scale because I don't want to draw it that big. But if I multiplied each of these sides by 3, I'd be able to try and draw it to scale. And a scale-ish. This triangle, 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15. This triangle is also a similar triangle. All three of these triangles are similar, even though they're not drawn in the same orientation, right? If you rotate and flip this one around, you could draw it in the same orientation as this, and they would look more like they're similar, but these are similar regardless of how we draw them. So if all the sides are in proportion to each other, that's one way of saying they're similar, or if all the angles are the same. So for example, I'm going to try and draw something, it might not look great. Let's say I have a triangle that looks like this. I'm not great at drawing angles that are not like nice angles, so bear with me here. I'll try and draw. I'm gonna make one of them right just because whatever. Let's say this angle here is, I don't know, let's say this angle is 40 degrees. This angle here is 50 degrees. This angle here is 90 degrees. These two angles always have to add to 90 because the angles of the triangle have to add to 180. So if I draw a smaller triangle, where the angles are the same, that's 40 degrees, that's 50 degrees, it's right angle. These triangles are also similar to each other. It doesn't matter that we don't actually know the side lengths. If we know all the angles are the same, the side lengths are going to be in the same proportion to each other. One way to think about that, I don't know what sine of 40 degrees is, but if I call, say, this side, let's use some smart letters here. I'm going to call this capital A, this capital B, this capital C. This is lowercase a, this is lowercase b, this is lowercase c. For example, if I look at sine of 40 degrees, I'm not actually going to plug them into a calculator, but I can see that it's equal to a over b, but it's also equal to little a over little b. Since these angles are all the same, we can see that these triangles are in proportion to each other because any ratio of any two sides is the same because the angles are the same. So similar triangles, either the sides are in proportion or all the angles are the same. And really one means the other. The reason I'm mentioning that is because we're going to talk about some special triangles where we want to be able to talk about kind of different sizings of them or different scalings of them. And I hate to waste a whole area of paper here, but I'm going, sure. So let's actually talk about the triangles. So the first triangle, we're going to start with a square. Okay, no, it's not a triangle. Start with a square, and let's say each side of the square has a length of 1. And we're going to cut the square in half so that we get a triangle, meaning I'm going to cut it diagonally. And we use the Pythagorean theorem to find the length of this side. Let's call it x for a second. So 1 squared plus 1 squared equals x squared. 1 squared is 1. 1 squared is 1. So I have 1 plus 1 equals x squared. 1 plus 1 is 2. If I take the square root of both sides, the square root of 2 is equal to x. So this triangle, which I'm going to draw like this, has side lengths that are 1, 1, and the square root of 2. Also, we know what the angles are. This angle is 90 degrees, right? Came from the square. And these two angles here, well, since I cut this 90-degree angle in half when I do this angle, each of these angles are 45 degrees. We can also see that because each of these sides is the same length. And so there's kind of a rule that when the sides are the same length, the opposite angles have to be the same too, but that's for another time and place. So, and I want to point out that this triangle, do I want to point that out just yet? No, I kind of just want to find the trig functions. So, oh, I will also, though, I'll mention that we can write it like this. You can also, though, see that you could call those angles pi over 4, because we learned yesterday, or we saw yesterday, that 45 degrees is the same as pi over 4. And that side lengths are still 1, 1, and the square root of 2. So let's find all 6 trigonometric functions of 45 degrees. All right, so sine of 45 degrees is 1 over root 2, opposite over hypotenuse. Or I could have said this angle opposite over hypotenuse, right? Either way, it's 1 over root 2, which I'm going to rationalize by multiplying by root 2 over root 2 and get root 2 over 2. And the reason I'm doing that really is because that's kind of the standard way of doing it. Similarly, cosine of 45 degrees is equal to adjacent over hypotenuse, which is 1 over root 2, which is also equal to root 2 over 2. To me, that's kind of the most notable thing about 45 degrees is that both sine of 45 degrees and cosine of 45 degrees have the same value. That's always true. Tangent of 45 degrees is going to be opposite over adjacent, which is 1 over 1, which is 1. And then the other 3 trig functions, the reciprocal trig functions, cosecant of 45 degrees is going to be root 2 over 1, which is just root 2. Secant of 45 degrees is going to be the reciprocal of root 2 over 1, which is just root 2. And cotangent of 45 degrees is going to be the reciprocal of tangent, which is just 1 over 1, which is still 1. So those are the 6 trig functions of one of our 3 special angles, 45 degrees or pi over 4 radians. I might do the next one in radians instead of degrees, just to kind of switch it up a little bit. Okay, so let's look at the next important angle. And then we're going to come back around and talk about, we'll do all 3 angles and then we'll come around, come back. So for the next important angle, we're going to take an equilateral triangle. So equilateral triangle just means all the sides are the same length. For a triangle, it also means all the angles are the same value. I will point out this square over here is an equilateral quadrilateral. It's also an equiangular quadrilateral because all the side lengths are the same and all the angles are the same. You could draw a rectangle though, where all the angles are the same and all the side lengths are, or you could draw a rhombus, a diamond, where all the side lengths are the same and the angles not the same. But for triangles, equilateral and equiangular happen to be the same condition. So this triangle, I'm going to make all the side lengths 2 because it's convenient. And I'm going to, well, all the angles have to be 60 degrees. And then I'm going to cut this in half. I'm going to cut it in half down the middle like this. So when I cut this in half, I get a new triangle. I'm only taking the left half, where this hypotenuse has a length of 2. This base here, I've cut this side literally in half, has a length of 1. And then we're going to use the Pythagorean theorem to find the length of the height. So let's see. 1 squared plus x squared equals 2 squared. 1 plus x squared equals 4. X squared equals 3. X equals the square root of 3. Great. So then we can label this angle as 60 degrees, this angle is 30 degrees. And you like to draw little like things like this, whatever. Or you could also label it using radians. So if I can label this, 60 degrees is pi over 3 radians, 30 degrees is pi over 6 radians. And this is 1, this is root 3, this is 2. The way I always kind of think about, oh, and this is pi over 2 radians or 90 degrees. The way I always kind of think about this triangle, and actually all triangles, is that the smallest angle is opposite the smallest side, the largest angle is opposite the largest side, and the medium angle is opposite the medium side. And root 3 is the medium side here because root 3 is between 1 and 2. It's approximately 1.73. So, and you can also draw it in a different orientation. Like I like to draw the angle I'm working with for some reason in the lower left-hand corner. That's just how I like drawing my triangles. But you could also redraw it like this if you wanted to. So that you had the smaller angle, pi over 6 up there, and pi over 3 over here, and still 90 degrees over here, or pi over 2 radians. And now this would be 1, this would be root 3, and this would be my longest side of 2. Cool. So let's go ahead and find all 6 trigonometric functions of, let's do it in radians just for fun, of the angle 60 degrees or pi over 3 radians. So sine of pi over 3 radians, it's going to be opposite over hypotenuse, which is root 3 divided by 2. Cosine of pi over 3 radians is going to be adjacent over hypotenuse, which is 1 over 2. And tangent of pi over 3 radians is going to be opposite over adjacent, which is root 3 over 1. Whenever you're dividing by 1, you just get what you divided into. So root 3 divided by 1 is just root 3, just like 6 divided by 1 is 6. And then the reciprocals, cosecant of pi over 3 is the reciprocal of that, and we do rationalize it. You don't always have to rationalize everything, but you will see these trig values specifically for these special angles rationalized. So we're going to get 2 root 3 over 3. Secant of pi over 3 is going to equal the reciprocal of 1/2, which is 2 over 1, which is just 2. And cotangent of pi over 3 is the reciprocal of root 3, which is going to be 1 over root 3. And yeah, we rationalize that as well. You don't actually have to show the step of multiplying by root 3 over root 3. You can, and you should if you feel like you want to. But if you know that you multiply by root 3 over root 3, the bottom just becomes 3. The numerator is 1 times root 3, which is root 3. Cool. So those are the 6 trig functions of 60 degrees or pi over 3. And now let's do the other one. So for pi over 6, but let's do it in degrees just to go back and forth. So now I want to do pi over 6 radians or 30 degrees. So for sine of 30 degrees, well, for 30 degrees, it's opposite over hypotenuse, which is 1/2. For cosine of 30 degrees, we're getting the adjacent over the hypotenuse, which is root 3 over 2. Notice that for these complementary angles, the sine and cosine values have interchanged. The sine value here is the cosine value here. The cosine value here is the sine value here. That is not a coincidence. That is happening every time. And then for, let's see here. Sorry. Apologies. We want tangent of 30 degrees. That's going to be the opposite of adjacent, which is 1 over root 3. We already know that 1 over root 3 rationalizes as root 3 over 3. So since we're kind of running out of space over here, let's write it as root 3 over 3. And then reciprocals, cosecant of 30 degrees is the reciprocal of 1/2, which is 2. Secant of 30 degrees is the reciprocal of 2 over root 3. And we know the reciprocal of 2 over root 3 is the reciprocal of root 3 over 2, which is 2 over root 3, which we know rationalizes as 2 root 3 over 3. And finally, cotangent of 30 degrees is equal to the reciprocal of root 3 over 3, which is 3 over root 3, or just root 3. So there we have it. So what to say about all this? Well, there's a few things. First, let's talk about these special triangles, because I do think they're worth memorizing, and there's probably 2 or 3 good different ways of doing that. So there are 2 triangles. We have our 45, 45, 90 triangle. We'll talk about first. Or it doesn't roll off the tongue quite as nicely, but you can also say your pi over 4, pi over 4, pi over 2 triangle. Isn't really like 45, 45, 90 is much faster than pi over 4, pi over 4. I can't even say it. Pi over 4, pi over 4, pi over 2. It's a tongue twister. So the 45, 45, 90 triangle, there are, in my opinion, three good ways of drawing it. Three similar triangles that all work just fine. So let me draw the one we started with first. Sure, I'm gonna go a little bit big here. I guess I'll try and draw these so they're actual size, but we'll see. So the one we did was 1, 1, root 2. And that's totally fine. But you could also scale this by whatever factor you want. And there's two particular factors I would like to scale it by. So one way of doing this is you can multiply each side by the length of the square root of 2. So I multiply this by root 2, by root 2, and by root 2. Root 2 times root 2 is 2. So if I multiply every side by root 2, I get a slightly bigger triangle. Doesn't actually matter that it's bigger. I could just draw it the same size and label it appropriately, but I'm going to draw it bigger. 1 times root 2 is root 2. 1 times root 2 is root 2. And root 2 times root 2 is 2. The reason someone might label it like this instead is because then it's very easy to see what sine, cosine, and tangent are without having to do any rationalizing. Sine of 45 degrees is root 2 over 2. Cosine of 45 degrees is root 2 over 2. Tangent of 45 degrees is root 2 over root 2, which simplifies down to 1. And then there's one more version of this that I actually think is particularly useful. I actually want the hypotenuse to have a length of 1. So if I divide all these sides by 2, I'm actually going to get a small triangle that's smaller than that. That's too small. But I did, again, sizes don't really matter here, but it's good to be kind of accurate. So root 2 divided by 2, root 2 divided by 2, and 2 divided by 2. All these triangles are similar. All these triangles have the same angles, and therefore they have the same trigonometric function values. So sine of 45 degrees in any of these triangles should be the same. Sine of 45 degrees here is 1 over root 2, which rationalizes as root 2 over 2. Sine of 45 degrees here is root 2 over 2. Sine of 45 degrees here is root 2 over 2 divided by 1, but dividing by 1 never changes anything, so you just get root 2 over 2. So there's three good ways. And the reason I'm really talking about this is because particularly writing it this way is going to be useful when we talk about the unit circle. Okay, let's look at the other one. Let's look at the 30, 60, 90 triangle. So 30, 60, 90 triangle, or less nicely said, the pi over 6, pi over 3, pi over 2 triangle. I know, it's just not as nice. So I'm going to draw it in the orientation I kind of like to prefer to draw it in, which is the smaller angle down here. But again, whichever way you want to draw it is fine. Just make sure that the largest side is always the hypotenuse. So this side here should be 2. And then for my 30-degree angle, that's opposite the side length of 1. And then for my 60-degree angle, that's opposite the side length of root 3. And that's the way I like to draw it usually, because it's like, oh yeah, sine of 30 is 1 over 2, cosine of 30 is root 3 over 2, tangent of 30 is 1 over root 3, which is root 3 over 3. However, I could also find a similar triangle by multiplying, well, I should say by dividing each side by 2. Because again, I'm trying to make it so the hypotenuse is 1. So these triangles are similar. In fact, let me write that over here. These are all similar triangles. And this triangle I'm about to draw is just going to be half the size of this one, proportionally. Again, not a perfect, right? These angles are not perfect. That's not actually a 60-degree angle. I didn't measure it. Just trying to make it look about right. And I'm going to say everything divided by 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. Root 3 divided by 2 is root 3 divided by 2. So just, right, these are also similar. And I can look at either triangle to find the trig functions. Sine of 30 degrees is 1/2. Sine of 30 degrees is 1/2 divided by 1 is 1/2. Cosine of 30 degrees is root 3 over 2. Cosine of 30 degrees is root 3 over 2 divided by 1. So they're really the same. I should say they're really similar triangles, and you can use any one of them to find the trig functions of whatever angle you want. So I think it's important to know what these triangles look like, whichever version of them you like. I'll talk about them in the future. And what I would say here is that, what do I want to say here really? What I want to say here is there's an expectation that you are able to evaluate the trigonometric functions of 30 degrees, 45 degrees, and 60 degrees, or pi over 6, pi over 4, pi over 3 radians relatively quickly. One way of easily doing that is memorizing what this triangle looks like and what this triangle looks like, and then being able to spit out SOHCAHTOA. Sines opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent opposite over adjacent. There are other ways of doing this. I'm going to show you one more thing about these special angles that I think is useful, and then we will we'll move along. We'll move along to maybe reference angles. We'll see. I'm debating in my head here if I want to talk about that or not. So one more way to think about these angles, which I think is useful. One pattern I've seen over the years. So if my angle is, I'm going to go from smallest to biggest. So, so I'm going to give you there's a word, the abbreviated version of this, because there's two angles I can't include yet, but this pattern is going to hold for two more angles that we're going to add in later. So the angles we're going to start with here are going to be 30 degrees, which is equal to pi over 6 radians, 45 degrees, which is equal to pi over 4 radians, and 60 degrees, which is equal to pi over 3 radians. And then we're going to write sine and cosine. So looking back here for a second, sine of 30 degrees, if I need to look at my triangle, and I could just, I should just draw it over here. So it's good to be able to draw this triangle on command. So 30 degrees, 60 degrees, 90 degrees, opposite 31, opposite 60, root 3, opposite 90, 2. And then I also need the 45, 45, 90. Ooh, it's not my best. 45, 45. And then I usually do it as 1, 1, root 2. So sine of 30 degrees is 1 over 2, which I am going to rewrite in just a second. Sine of 45 degrees is 1 over root 2, which rationalizes as root 2 over 2. And sine of 60 degrees is opposite of hypotenuse, is root 3 over 2. And what I want to point out is these kind of follow a pattern if you do one thing. If you rewrite 1/2, although I would always leave it as 1/2 actually, but if you think of 1/2 as the square root of 1 over 2, then we can see that sine of an angle, 30 degrees, 45 degrees, or 60 degrees, is just the square root of either 1, 2, or 3 all over 2. And the numbers inside the square root increase by 1 as you increase from one important angle to the next important angle. And the cosine, it's the reverse. Cosine of 30 degrees, you get the square root of 3 over 2. Cosine of 45 degrees, you get the square root of 2 over 2. And cosine of 60 degrees, you get 1 over 2, which is equal to the square root of 1 over 2. Again, there's kind of this nice pattern of, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. And that pattern does extend to two more angles that we'll talk about later. So that's one way of also remembering it. It's not what I usually do, but it is a way that works. Let's see, there was something else I wanted to mention here. Oh, I know this. The other thing that I've noticed about sine and cosine over the years is that these two values always get paired together. So if your angle is 30 degrees, one of them is 1/2, one of them is root 3 over 2. If your angle is 60 degrees, one of them is 1/2, is one of them is root 3 over 2. So if you know that either sine or cosine is root 3 over 2, then you know the other one is going to be 1/2 and vice versa. Reference angles. Reference angles. Do I want to talk about reference angles? Kind of. I'm already 24 minutes in. Yeah, let's go ahead and talk about reference angles. It'll be brief. It's a thing that's fast to talk about, that is easy to do. So what is a reference angle? Well, let me give you an example first. So let's say our angle, let's say theta is, I don't know, 160 degrees. What's the reference angle? What is the reference angle? Well, if I draw 160 degrees in the standard position, it looks like this. And the reference angle is the acute angle that is made with the terminal ray and the closest x-axis. So not this side, because that's not the close side, this side here. So this angle right here, which is 20 degrees, that angle is my reference angle. Answer, 20 degrees. So general, and so we can write a definition if we want. So reference angle definition is going to be, it's kind of long, whatever. You don't need to, like, I'm giving you definitions because I feel like I owe them to you, but you just have to have the idea of how it works. So for an angle in standard position, the reference angle is the acute angle, meaning an angle that is positive, can't be zero, and strictly less than 90 degrees, can't actually be equal to 90 degrees. Measured between the terminal ray and the nearest x-axis. Cool. So if I was actually doing this one, I would note that over here, the angle to the x-axis is 180 degrees. And all the way around, this is 360 degrees. So if I actually wanted to calculate this, like using math, I would say, oh, my reference angle is equal to the difference between 180 and 160, which is equal to 20 degrees. What if I was using radians? So now we're just going to do a bunch of examples where I'm going to give you an angle and we're going to find the reference angle. So given an angle, let's call it theta because that's typical, find the reference angle. So let's say our angle is theta equal to 3 pi over 4. Ooh, radians. So for radians, it's a little bit harder to know right off the bat what quadrant your angle is in. You don't have to draw it, but I find it helpful. So 3 pi over 4, well, over here is 0 radians. And I go halfway here. Here's pi, which is equal to 4 pi over 4. And then all the way around is 2 pi. So I'm going to go 3 pi over 4. Well, that's going to be right about there. So my reference angle is going to be this angle here. So my reference angle is going to be the difference between pi and 3 pi over 4. So it's going to equal pi minus 3 pi over 4, which is going to be 4 pi over 4 minus 3 pi over 4, which is pi over 4. Cool. Let's do some more examples. Let's say my angle was, we'll do 1 in radians, sorry, 1 in degrees and 1 in radians. We'll go back and forth. So let's say my angle was, I don't know, 210 degrees. So now I know the 210 is in quadrant. I know we haven't talked about the quadrants. I'm just going to say, right, quadrant 1, 2, 3, and 4. 210 degrees is in quadrant 1. Quadrant what? Quadrant 3, because it's bigger than 180 degrees, less than 270. So whenever I'm drawing my XY coordinate system here, I'm always thinking of this being 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then all the way around is 360 degrees. So 210 degrees is a little bit more than 180. There's my 210. My reference angle now looks like this. There is my reference angle right there. So here, if I calculate my reference angle, it's still the difference between 210 degrees and 180 degrees, but the subtraction has to go the other way, right? When I did this previous one, when it was the angle was in quadrant 2, I did 180 minus 160 because 180 was the bigger angle. But now, if I want to find the reference angle here, it's going to be 210 degrees minus 180 degrees, which is going to be 30 degrees. If you ever subtract in the wrong order, you'll get a negative angle, which we know a reference angle can't be because the reference angle has to be an acute angle, which must be positive. Okay, let me throw in another one over here. Let's say my angle theta is equal to Sure, we'll go kind of exciting here. Let's say the angle theta is, I'm trying to think of an interesting example. Let's say it's 13 pi over 9. Yeah, 13 pi over 9. I really don't want to convert it to degrees. So I'm just going to remember that here's 0 radians, here's pi over 2 radians, here's pi radians, and here's 3 pi over 2 radians, and this is also 2 pi. 13 pi over 9, definitely bigger than a whole pi, but is it less than 3 pi over 2 or not? Well, I might actually do something where I multiply it by 2 over 2. So this is equal to 26 pi over 18. I know that pi is equal to 18 pi over 18. So that's certainly 26 is bigger than 18. And 3 pi over 2 if I multiply by 9 over 9 is equal to 27 pi over 18. So 26 pi over 18 is going to be not quite into the 4th quadrant. It's going to end up in the 3rd quadrant. So there's my 26 pi over 18, which is really just 13 pi over 9. And then my reference angle is right here. So my reference angle here is going to be my angle, 13 pi over 9, minus the angle for the closest x-axis, which is going to be minus pi. But pi is really just 18 pi over 8 or 9 pi over 9. So I get 13 pi over 9 minus 9 pi over 9, which is 4 pi over 9. So far, here's what we're seeing. If your angle happens to be in quadrant 2, you're going to do 180 minus it, or pi minus your angle in radians. If your angle happens to land in quadrant 3, you're going to do your angle minus 180 degrees, or your angle minus pi radians to find the positive reference angle that's acute. Finally, let's do 2 more examples and call it a day. Let's say our given angle is theta equal to 283 degrees, which I know is bigger than 270, but not as big as 360. So it's going to be right about there. And then we know that the reference angle is going to be this leftover amount here. So our reference angle is going to equal, well, I need the difference between 360 degrees and 283 degrees. Reference angle is going to equal 360 degrees minus 283 degrees, which is going to be 60 plus 17, it's going to be 77 degrees. Or in radians, we're given, say, theta equal to, I'm trying to pick examples that are not, well, let's just do a normal one. Let's say theta is equal to like 5 pi over 3. So here's 0, pi over 2, pi, which is 3 pi over 3, 3 pi over 2. So 5 pi over 3 is the same as 10 pi over 6. And then pi over 2 is really 3 pi over 6. 3 pi over 2 is really 9 pi over 6. So 10 pi over 6 is a little bit bigger than 9 pi over 6 or 3 pi over 2. So I'm right there. So my reference angle, again, measuring to the closest x-axis, always the x-axis, is going to be, well, that's 5 pi over 6. Sorry, 5 pi over 3, apologies. So I'm going to do 2 pi minus 5 pi over 3. Which I was going to do it in red. Oh, well, sorry. My reference angle is equal to that, which is going to be 6 pi over 3 minus 5 pi over 3, which is just pi over 3. So that is a brief explanation as to how to find reference angles. You're always just finding the positive difference between your given angle and the nearest angle for the nearest, I should say, the angle for the nearest x-axis. So if it's this x-axis over here, the angle is 180 degrees or pi radians. If this is the nearest x-axis, it's 2 pi radians or 360 degrees. And that's really mostly it. All right, I will see you all tomorrow. Bye.